Hello everybody, we return to our lecture series on algorithm design using dynamic programming, and we move to the next lecture, the second lecture of the series. Just a quick overview. Dynamic programming consists of a recursive definition, exploration of the properties, and then the main analysis is identifying identical subproblems and memoizing the past solutions and reusing these memoized values so that we solve every identical subproblem only once. And that leads to this dynamic programming philosophy, which has got its basic tenets as a recursive formulation, which has got optimal substructure, and then we have evaluation, which consists of the following parts. There is a memoization, that means we store values and reuse them. So there is store and reuse, so that we don't have to compute them many times. And then we have a top-down evaluation, which we have discussed, and in many cases we can have an iterative evaluation, which we can also see. Finally, we would require any special data structures which may be there in addition to the memoized data structures. So it falls in our generic scope, and we have discussed the matrix chain multiplication, the Fibonacci series, and many other series. Today we move on to examine string matching problems. String matching problems arise in many places. For example, one of the string matching problems are considered to be the pattern matching in a string. In a text. That means, given a text string S, which is a string of characters, and a pattern P, which is a string of characters, our interest is to find occurrences of P in S. This is a typical problem which is found in a large number of text, where given a text file, we want to find out whether there is a pattern, and we have, all of us have used this. And here this pattern matching in a text could be A, it could be an exact match, or it could be an approximate match. And this approximate match may come with one error or two values exchanged and things like that. And we have many applications of this, and there are several ways in which you can solve such problems. For example, if you had a text which was just as a sample, suppose this was my S, and suppose my pattern P was then we can see that this is the occurrence of this pattern in this string. There could be multiple occurrences. For example, if S was A, B, A, B, A, B, A, C, and my pattern was A, B, A, you can see that there are multiple overlapping combinations where the same string occurs. The other problem, which is typically a pattern recognition problem but of a different kind, is what is usually known as the sequence alignment problem. And in the sequence alignment problem, you are given two strings and you want to find out how closely they match each other, irrespective of whether there are some partial mismatches. For example, suppose you have this word interaction and you have another word called contradict. Then we would like to find a sequence of letters in X. Let us have two such strings, X and Y. We would like to find a sequence of matches here. For example, we know that, and this sequence of matches could be contiguous or could have some intermediate letters which do not match. So in the typical sequence alignment problem, we would like to have what is the common sequence of them. For example, we know one common sequence for both of these two is N, T, R, A, C, T. As you can see, N, T, R, A, C, T is here. Here you have N, T, R, A, C, T. So there is a sequence of letters which match. There are other sequences which match also. For example, C, T, I. This is a match. Another match is N, T, R, A, I. These are all matches. And we would like to find out either all matches. So we would like to find out A, all matches of length greater than equal to K, or we could find out the longest match. The longest match problem is known as the longest common subsequence. And this problem of sequence alignment comes in protein sequence alignment. In biology, we have a mechanism where we represent a protein alphabetically in terms of these four letters A, T, C, and G. And we have these protein sequences, and we want to find out how such sequences have common segments of match. For example, if you had a protein sequence which was C, G, A, T, A, T, T, G, A, G, A, and you had another sequence, so if this was X, and you had another sequence which was Y, which was G, T, T, C, C, T, A, T, A, then you can find out that a common subsequence of these two, the maximum common subsequence of these two would be TAA, then one more T and one more A, or here it would be CTAA TA. So the CTAA TA in Y matches a sequence in X, and that is the longest subsequence here. And there are several variations of this protein problem, and as we can see, there are proteins of millions of length size, and how do we solve this problem intelligently? Then this also forms part of a larger category of problems which are known as the edit distance problems. A more generalized formulation of sequence alignment problems of several variations is known as the edit distance problem, where we try to find out strings which have a mismatch. There are several other variations of such problems, and we would be interested to look at some of them in this lecture. The first, as we just mentioned a little while earlier, is the exact pattern matching problem. And the exact pattern matching problem is this problem. A problem where, given a string like a text file and a pattern, we want to find out the occurrence of the pattern, either the first occurrence or all occurrences. And in order to solve that problem, in our mechanism, we would first write out a recursive definition. So what would the recursive definition be? Given a string S, which is of S1, S2, right up to Sn, let us write it down properly, Sn, and a pattern P, which is of the type P1, P2, Pm. Obviously, we know that m should be less than or equal to n. We would like to find out whether there is a match. If m is equal to n, all we need to do is to check element by element. But since we have seen the example here that we have seen, so what we would like to do is we would like to find matches, and a basic recursive definition, a very straightforward naive recursive definition would be as follows. Match SP, and we would first check if any case the size of S is less than the size of P, then we return failure, we return false. That means, let us say we return 0. Since we are checking sequence by sequence, if P has become empty, then we say that we have succeeded in finding a match, because we have completed all elements of C and found some match of P and found some matches in S. Otherwise, we check the first instance. If S1 is equal to P1, then we match the rest of the two strings. That means the first elements are matched. So we will return match of S minus S1 and P minus P1. So if the first elements match, then we will match the rest of the elements. If the first elements don't match, then we have to check whether P matching starts from S2. That means we then again call match and check whether We remove S1, but since P1 has not matched, we run it for the whole of P. And if this is the case, we have the algorithm. It's a straightforward algorithm, and as you can see, this is an order n into m algorithm, where every starting point from S is checked for every element of P in the worst case. And this recursive algorithm can be easily converted into iteration. While pattern matching is a standard problem, and we shall have a separate detailed lecture on pattern matching, the objective is, can we do better than order n into m? And the reason to do that will come from a very simple case study that we have. So in our case, suppose S is A, B, A, C, A, B, A, B, A, C, A, and P is A, B, A, B, A, C. If you check that the first element that matches, if we start from this position, then the two A's match, but the next element B does not match. Once the next element B does not match, when we have come to start from here, then we know that this A, when we have this A, we can start from here, and when the next B matches and we come to the next A, we know that we don't need to go back and start right from the beginning. So once there is a mismatch, where to go back and start, that pre-processing data structure can be created. For example, in this case, how would that pre-processing data structure look like? The pre-processing data structure would look like this. We draw up a state machine as follows. We draw up the start state. We draw up the state saying that this is my string A. It goes to state 1. Then B. I'm drawing up a state machine with the pattern. Then A. Then from here it will go to A, B, A, then B, state 4, then from state 4, from B, again A, state 5, and from A to C, state 6. Suppose this is the sequence I want to match. Now, let us try to find out how we will draw up this state diagram. Now here, we know that if we get B or C, we remain here. That means this is my starting point. Now, the most interesting thing is, at this point in state 1, if I get A, then I know that I have already got an A, so I don't need to start from the beginning. I know that I have already matched an A. So if I get an A, I know I am still here, because I have already, in state 1, I am supposed to get B to move to state 2. If I get A, then I know that I have received one A. That means my prefix is already A, therefore I remain in state 1. On the other hand, if I get C, then I move here. That means I have to start again from the beginning of the next element of the string. In the next element of the string, since it has not matched and I have got a C instead of getting a B, then in my pattern, I have to start my pattern right from the beginning. Again, if I have reached B here, and then in B, if I get A or C, then I have to move to another location. So if from B I get A, then obviously I will move, sorry, from B to A moves to state 3. So if I get C, the only thing I can get is C, then I will again have to restart from the beginning. Again, from state 3, I am supposed to get a B to go to state 4, but I could get A or C. If I get A, that means that I have to start all from the beginning, so I will come here, because here it means that state 1 is a state where the prefix is A, state 2 is a state where the prefix is AB. Now if I get a C in state 3, again I have to move back to state 0, which means that I have no prefix, because nothing starts with C. There is no prefix with C in one state. If I get C, actually I am reaching my final destination. Again, when I have got A, B, and I am supposed to get A next, but if instead of A, I get B or C, sorry, here also, if I get B or C, then again I have to move here. Here also it was B or C. In state 2 also, instead of getting A, I got B or C. In state 3, if I got A, I moved to state 1. If I got C, I moved to state 0. In state 4, whether I get B or C, I move here. In state 5, if I get B, please note in state 5, when I'm supposed to go from here and supposed to get C, suppose I get B, then I know that I can move back to this state. So here instead of C, if I get B, then I know that I have got A, B, and again if I get B, then I already have the sequence A, B. So I will move to this state. This state means that my prefix till now has been A, B, I'm here. So I've got A, B, which means that I have already got a, so here if I get B, then I am actually equivalent to this position, which is the state 4, which is AB position. So here if I get a B, it is equivalent to having a prefix AB, that is why I move to this state. On the other hand, if at this position instead of C, if I get an A, then I have to move to the state 1. So by drawing up a data structure, based on pre-processing of P, I am able to reduce the number of places that I move back, and using this strategy we can develop many faster algorithms for such exact string matching. And one of the most famous algorithms that use this is called the Knuth-Morris-Pratt or the KMP string matching algorithm, which will yield to an order n plus m algorithm. I will not do it there. I just wanted to highlight how from our original algorithm we can do an order n m pre-processing to develop this data structure called a deterministic finite automata, which will help us reduce significantly the number of steps I need to go back onto the string as I move ahead. So I will just scan the string once, I will scan the pattern once and get a more efficient algorithm. We will do string matching in more details and pattern matching in more details in a separate lecture. With this, we move back to our maximum common subsequence problem. As we had said before, our example was like this. Suppose we had x1, x was the word interaction and y was the word contradict. Then we had the following options. Z1, a common subsequence was a second common subsequence Z2, third common subsequence maybe, and other subsequences will be of smaller length. Again, in biology, we will have a string S1, a sequence S1 of proteins was C, G, A, T, A, A, T, T, G, A, G, A, and maybe S2 was G, T, T, C, C, T, A, T, A, and this is a common portion which occurs G, C, T, A, T, A. There could be many other matches, but this is the longest common subsequence. For example, this is the longest common subsequence of the previous one, and this is the longest common subsequence here. Now, we could have several other variations of this problem. We could want to find the longest common subsequence. We could like to find all common subsequences of length greater than equal to k, or length which is equal to 1 minus epsilon, or length which is greater than equal to 1 minus epsilon of the LCS. That means within 1 minus epsilon of the. So we would like to find those whose length is greater than equal to 1 minus some epsilon of the LCS. That means as many such strings of long value. We could also look at, here we have only looked at strings which are contiguously matching. So this involves the associative property. We could also look at certain mutations, or we could look at commutativity. And based on such stuff, we will end up in a more general formulation. And this more general formulation comes under the category of edit distance. And we shall briefly discuss the edit distance. But before we proceed, let us now look at the way in which we try to solve the longest common subsequence problem. So how do we formulate the longest common subsequence problem? We go back to this exact string matching problem and we see that we will do the same thing, almost the same thing here, but our base conditions and certain other conditions will be different because we are not looking at an exact continuous match. We are looking at matches which can have gaps between them. Like we see here, NTRACT, here is NTRACT, here it is NTRACT. So there could be gaps. So we have to take care of the gaps. So in order to take care of the gaps, our method will again involve a recursive definition. So what will be our recursive definition? So LCS XY, we will say that if any one of them is null, we return null, because if any one of them is null, there is no common subsequence to return. So if X equal to null or Y equal to null, return null. There is nothing to match. Otherwise, let X be X1, X2 up to Xn, and let Y be Y1, Y2 up to Ym. Then again, like we have done in that earlier matching, we check if X1 is equal to Y1, then we compute Z1, which is X1 concatenated with the LCS of X minus X1, X minus X1, Y minus Y1. Because if the first strings match, then if that is part of the longest subsequence, then obviously we just have to do that. However, and we return Z1. However, if this case does not occur, that means if there is an else part, then for the else part, we will have to look at either removing an element from X1 and seeing whether there is an alignment of the remaining, or removing it from X2. So we will compute Z2 equal to LCS X minus, we remove X1 and match with the full of Y, just like we did in the pattern matching. Or now, since it's a two-way issue and we don't need an exact match, so compared to this pattern matching problem where we did exactly up to here is similar to what we have done, but since the pattern need not be exactly matched and it's a two-way problem, so we have to look at the other option where X remains intact and from Y we remove Y1. And among these two which happen, we find out Z is equal to max of Z2, Z3, and we return Z. This completes the else part and completes the program, which means that if I had these string, let us say interaction and contradict, then we would match the first two elements, and we would, since they do not match, then we would call it on these two parts in the else part, we would call it with, from Z2 we would call it with x equal to and y equal to contradict, and for Z3 we would leave x as the same as and y we would make it as, because they have not, because their first characters have not matched. But suppose it was, instead of this sort of example, suppose the example was yet and y was yes. Then, since the first characters have matched, we would not need to compare any other thing. We would then try to find out the longest subsequence between ET and ES, and then whatever is the result, we would concatenate with y, and that would be the longest common subsequence. So these are the three cases. And if you open up this recursion, it is not difficult to see that identical subproblems will significantly arise, because this is very similar when I take x minus x1 y and x minus y1, then at some point in time I will get back x minus x1 and y minus y1 from either the either from here I will get back something like this, or from here I will again get back something like this. So as you can see, there will be a lot of identical subproblems, and you can easily draw up the recursion to show that there will be an exponential growth. It is also easy to prove this by induction. So now, since there are these identical subproblems, we would now like to use our dynamic programming paradigm to solve this problem. So in order to push it into the dynamic programming paradigm, we simply we go back and write this down in a simple equational form. So we have LCS. We stored xi. I am in x at the xith position. I am in y at the yith position. We say 0 if either I is equal to 0 or j is equal to 0, which is identical to one of them being empty. This, next we check whether x1 and y1 match. So we will say is equal to LCS. This is now computing only the length. X I minus 1 y j minus 1 plus 1 if x1 xi equal to yj. That means if the first elements match. Otherwise, if two elements match, and obviously and I greater than 0, j greater than 0. Otherwise, we have to find the maximum of x I minus 1 yj. Sorry, we have to call LCS. So we find the maximum of what we will call LCS x I minus 1 yj, comma LCS x I yj minus 1. So with this we formulate the value. Here in the previous one we are getting the complete string. In this dynamic programming formulation we are only looking at getting the value. And in order to get this value, once we have the value, we know from where the value came. We will either know it came from this part or which of the ones brought out the max. So we will find out which way to go. So in order to do this, we have to memorize. And what do we memorize? We memorize everything that we have been able to learn. That means suppose x is hello and suppose y is yellow, then we all know that the maximum common subsequence is this. So what we do is we create rows corresponding to so for every we create this matrix which corresponds to H, E, L, sorry. So this will be H, E, L, L, O, and we create Y, E, L, L, O, W. We create this matrix, and every row of the matrix will be this, for example, this cell of the matrix. This cell of the matrix will store the LCS of HEL with YEL. So this will store LCS XI YJ. This is what it will store. Once we know that this stores LCS the way we want, we will then be able to find the final solution at this point. And once we have the final solution at this point, we can apply our top-down or we can apply a bottom-up formulation. The top-down formulation comes straight from the equation in the left side, and we will memorize this array and we will initialize all the values to be -1 except for these rows at 0 rows and the 0 columns. So we will initialize that to -1 and otherwise we will compute. Now and then we can compute it by a top-down algorithm which will automatically take care if we follow this recursive step. On the other hand, if we want to develop a bottom-up algorithm, then how will we develop? We now know that any value here, let us say this value, is dependent on these values. So this value can be computed from these three values. This is the first value, I minus 1, j minus 1. So this is I minus 1, j minus 1. This is I minus 1, j, and this is I, j minus 1. So these give me my z1, z2, z3. I am supposed to take the minimum of z1, z2, z3, but I know that if z1 is true, then it will be minimum anyway. So that is why I have separated it out. So now in order to evaluate this, the top-down algorithm will be taken care of by the recursion. The bottom-up algorithm, I have to decide on the sequence in which I will do. So I could do it row-wise, I could do it column-wise. So I could do it this way. I could do this, then this, then this, then this. Because when I compute this one, I have computed its predecessors. I could also compute it column-wise. I could do it this way. Or I could compute it diagonal-wise. So I could choose any of the methods to do an iterative algorithm. So we will now choose the row-wise method and develop the iterative algorithm. So now we will develop the iterative algorithm. As just mentioned, we will do this iterative algorithm row-wise. We will first initialize the first row and the first column to all zeros as per the definition, and then we will work out the whole method. So our LCS iterative algorithm, LCS iterative, will be as follows, where we have already maintained that global array, where we will use this global array Lij. This Lij is the memoized global array which we use here. So this is Lij. And how will we write it down? We will write our base steps for I equal to 1 to n. We will initialize Li0 to 0, and for j equal to 1 to m, L0j equal to 0. So this initializes the first column. The first one initializes the first column, the second one initializes the first row. And then if we go row-wise, then we will write down a double loop. And all we have to do is implement this recursive equation. And in order to implement this recursive equation, we will say if xi equal to yj, where we have stored x and y in that area, we now calculate Lij, since they have matched, is equal to Li minus 1 j minus 1 plus 1. Else Lij will be max of Li minus 1j comma Lij minus 1. So this is an iterative implementation, and as you can see, this iterative implementation is of the order of n into m complexity. The top-down algorithm will also do n into m complexity. It is easy to see why. It is an n into m array that we remember, and this n into m array, each row of each cell of the n into m array has to be filled, and based on the testing of the condition that we have, there is only one condition to be tested, and there are, if that condition is satisfied, xi equal to yj, then we have one computation. Otherwise we have two computations, which means that we can fill up every cell in constant time. and in order to fill up every cell in constant time, we can easily solve the problem. So let us look at the example that we have, and let us quickly see how we are going to solve our example. So we had hello and we had yellow, and we are going to create this so this corresponds to this corresponds to H, E, L, L, O, and here again we have and this corresponds to Y, E, L, L, O, W. And as you can see, this being symmetric, the row and columns can be interchanged, and even the elements can be reversed. Whichever way we do it, it does not matter. We will find the right solution. So how do we start filling up the values? So initially, by our initialization, all of this is set to 0. And once all of this is set to 0, then we move row wise and we check whether H and Y match. H and Y don't match, so we cannot take the diagonal element, which is I minus 1, j minus 1 plus 1, but we have to take either the left side or the top and the max of the two, which remains 0. Similarly, H does not match with E, H does not match with L, H does not match with L, H does not match with O, H does not match with W. Next we come to E. E does not match with Y. So since E does not match with Y, this comes. But now the row 2 and the column 2, E and E match. Since E and E match, we will use the first part of the equation, where we will take from the diagonal, and this will be 1. And once this is 1, we have marked that this is what we have chosen. Next, the next row will again have E does not match with L, so the diagonal will not be taken. So it will be taken as the maximum of either the same row left one or the top element, and we see that we will get 1, and we mark it out which one. And this marking we can do as a separate marker. We can keep an other than Lij, we can keep another Pij, which will mark what is the best value from which this value has been derived. So we can now see that these values will all become 1, and each of these will be marked this way. Similarly, we now come to here. So this will not match, L will not match with Y, so this will be 0. L will not match with E, but this will be 1 because it will be derived from its parent. Now L and L will match, so it will be derived from the diagonal, and we will get 2. Similarly, L and L will match, so we can get it either from this side or from this side. Any one of the two sides you will get 2. Then the next one will be 2 because O, 2. So we are marking the pointers like this. Now again we have L, so we will get this as 0, this as 1 coming from its parent. Then the next one, where L and L again match, this will come as 2. It can come from this diagonal or it can come from this parent. And this backtracing will yield us the solution. Now this L in row 4 and the L at column 4 will yield 3 because it will come from this diagonal, because the L's have matched. Now since this has matched, this will be 3 and this will be 3, and these will be pointers like this. Finally, O, this will not match. With E it will be 1. With L it will be 2 because it will come from this, from this. With L again it will be 3. It will come from this. But O will match with O and we will get 4 from this diagonal. And finally we will also get 4 here. So once we get this, we know that the maximum common subsequence is here. And in order to retrieve this, we use the pointers, and from the back pointers we will be able to calculate the sequence through which we will obtain our final goal. And this sequence will really tell us that the common matches that have occurred are at E, are at L, are at L and at O, and from here you will know that E, L, L, O is the maximum common subsequence. So this is how this algorithm works, and this algorithm, as we can see, works in order nm time, so order nm space as well. I leave it to you to think whether the space itself can be reduced. Now we come to the generalization. Let us come back to our original example of yellow and hello. So let us come to what is known as the edit distance. So let us come back to our example of x is equal to hello and y is equal to yellow. While the maximum common subsequence was one kind of a problem, the other kind of a problem that we need to solve is sometimes there may be spelling errors, or there may be letter switches, there may be typos. So we are looking for a general approximate match. And how do we do that? We say that if this is hello and this is yellow, we could apply 3 kinds of things. When we get Y and H, we could, if they don't match, if they match we know what to do, because we know that they have matched, so we move on to the next. But if they don't match, then we could substitute H by Y, or we could delete H, or we could insert Y. So we want to see how we will transform hello to yellow. So we are looking at transforming, suppose this is S1 and this is S2, we are looking at transforming S1 to S2 using insert, delete, substitute operators. and we will assign costs to each one of these operators. And once we assign costs to these operators, we will be able to determine. So we will have costs for each of these operators. Insert, delete, and substitute. So we will allow delete on S1, insert Y from S2 into S1, and substitute the elements. So let us take a case study example. Let us say our insert cost is 1, delete cost is 1, and substitute cost is 2. Then if we convert hello to yellow, then our sequence could be insert Y, delete H. So if I do insert Y and delete H, then in hello, if I insert Y, then I get YHELLO. Then I move here. Once I move here, I have to delete H. Then I get YELLO. Then I have a match with E and E, because here it was hello and yellow. Here I have inserted H, so I am now left with. So now once I have removed H and I am left with, now match. So I will get YELLO, and this becomes LLOW. Then again match, and match costs are 0. So for us, match cost equal to 0. So once I have this, then again L will match here. So I was here. Now L will match. So this will become YELLO. I am at this L. Sorry, here one L is less. And this will become LOW. Then again I will match. And this will become YELLO. It will be at O. This will be OW. Now O and W will match. So I will then move over and I will get match. And this will become YELLO. And I am at the end of this, and this is W. And now I will apply insert W. And once I insert W, I will get YELLOW, and this becomes null. And when this becomes null, I have completed the return. And if we calculate by doing this, I have used one insert here, one delete here, and one insert here, the matches. So there are two inserts and one delete. And if my cost is 1, then the cost here would be 3. On the other hand, in the beginning itself, I could have substituted Y with H and with a cost of 2 and continued. And I leave it to you as an exercise to see. I could vary the costs of insert, delete, and substitute. And if I vary the costs of insert, delete, and substitute, I will get a variety of functions. And with this generic variety of edit distance, I can try to solve a large number of problems. So in order to do this, we now generalize our maximum common longest subsequence into edit distance. And it is easy to see, and I leave it to you as an exercise to see what costs we should give to insert, delete, and substitute to make it reduce to a problem of maximum longest subsequence. Here our objective is to find the solution of minimum cost, whereas in the maximum common subsequence I am finding the solution of maximum length. So I will convert a maximization problem of longest subsequence to a more general edit distance problem where I am going to minimize the costs. So how do I now reach my formulation? So in my formulation, I leave it to you to develop the recursive formulation, but very quickly I will do the following. I will say for all I, di0 is equal to the summation of all the del i's. That means the first row, okay, so let us get our table, and from the table it will become clear as to what we want to do. So again we will develop the recursive equation and we'll write d0j will be the sum, because from j I can insert, from the first element s1 I can delete, from the second element I will insert. So this will be k equal to 1 to I. So for each of the elements, for the first element I have deleted the first one, in the second element I0 I have deleted the second one, and so on and so forth. So I am going to incur those costs. Similarly, this k equal to 1 to j will be insert j. And the recursive equation again will be very similar to the maximum longest subsequence. So dij will be equal to di minus 1 j minus 1 if xi equal to yj. That means if the characters match, it is the match, then obviously cost is 0, and since cost is 0, we need to find only the remaining part of the string. Otherwise, we will have to either do di minus 1j plus the cost of deletion, or di j minus 1 plus the cost of insertion. And in general, that deletion could be, each of these costs could be different. Which one I will insert, which one I will delete, all that could be there. And I have the third cost here, which is substitution. That means I could remove both plus substitute ij. And I have to take from these three, I have to take the minimum. So this is the generalization of the longest common subsequence problem. And if we generalize the longest common subsequence, we will get this equation. And we can write it down as a full recursive formula, as a recursive piece of code. And we can write down the top-down recursive code as well as the bottom-up recursive code and get our algorithm. But I think it is a straightforward thing for all of us to do. And to get this algorithm, the algorithm will be almost identical to the algorithm that we have written for LCS, only the appropriate equations shall be used. So I am not writing out that algorithm, but I will just like to work out the solution. So here again we are going to have, the match of yellow and hello. So we will write down YELLOW. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Again here we will have H, E, L, L, O, and this is 1, this is 2, 3, 4, 5, and we will apply the same sweep algorithm. We can do row wise, we can do column wise, and the initialization steps, as we have just mentioned, the initialization steps, this will be 0, 1, 2, 3, 4, 5, 6. That means here in y1 I have assumed here, let us assume the costs are insert is equal to 1, delete equal to 1, and substitute equal to 2 for all cases. Suppose if that is the situation, then we will see what are the best options that we have. Let us put substitute equal to 3, 2 or 3, whatever, it does not matter. So here what will fill up? We will fill this one up as also all zeros. Sorry, not zeros. This will be as per this definition, sigma 1, 2, 3, 4, 5. And then we will fill up this row. So this element, because these two don't match, this could either be the delete cost from here, or the insert cost from above, or the substitution cost from this side, and in any case, in all the three cases, it will be 2. Similarly, we can see this will be 3, this will be 4, this will be 5, 6, 7, because nothing matches. Then again, E does not match with this, so this will be 3. On the other hand, this E matches with column 2E, so this will come from this, and since there is a match, and in a match there is no cost, this will become 2. Once this becomes 2, you can see this will become 3, this will become 4, this will become 5 and 6. Now L, so here again we will have this will become 4 because L does not match with Y. This will become 4, sorry, this will become 3 because it will come from the top, whereas this came from here. This row L and E will come from the top, it will come from one more element will come from the top, and an insertion will happen. And once this happens, then we see this L and this L match, so this cost will again become 2 because it will come from this diagonal. Once this cost becomes 2, this becomes 3, this becomes 4, and this becomes 5. Now this L will not match, so this will become 5. This L will not match with E in the second column, so this will become 4, which will come from its top element, an element on its top. Now L will match with L, and this will again become 3. Either it will come from the diagonal or it will come from the top, based on the equation that we have here and the costs that we have defined. Similarly, this L will now come from here, and this L will become 2. Once this L becomes 2, because it will come from this diagonal, this will be 3 and this will be 4. Finally, this will be 6, this will be 5, this will be 4, this will be 3, and this O and O will match. Once O and O match, this will become 2 because this and this match, and this will be 3. And finally, as we have seen in the example previously, the final cost that we get is of cost 3, and this cost 3 will be computed by this algorithm. And as we have seen that this can be implemented in order m into n time and order m into n space. This additional space, this is the memoized space. And it is not difficult to calculate how many times we are reusing a particular computation. Now this formulation can vary. This formulation can vary where we can allow even exchanges. So we could have So we have done this dynamic programming. So there could be several variations to this problem. The variations could include more operators like exchanges in rows or commutativity, because in many typos people write THOUHG. Sorry. So sometimes we write by a typo THOUHG, where we have made this mistake instead of writing THOUGH. So this sort of operators where we can exchange to get back or switch to get back, we could also implement it by insert delete, but we could also implement it by other operators. In general, we could have various kinds of approximations, of approximate matches. That means we could have matches where we say that certain segments of the string match other than the costs and things like that. Then we could have multi-dimensional matching or alignment. That means we could look at 3 strings, 4 strings, 5 strings, n strings, and in bioinformatics we are typically interested in an alignment of p such strings. Now this would lead to a p-dimension array and an algorithm of the order of n to the power p. And how do we approximate that to a faster algorithm? These are all practical issues that come into the picture. Issues that come into the picture when we are solving several such other dimensions of problems. In the case where we are required to switch elements, we are required to find out whether these multi-dimensional elements can be mapped into a single array and things like that. So we can have several such data structures. So there are other data structures like hash tables. So when we do hash tables, we will see how these hash tables can also be used in order to solve this problem. With this, we come to the conclusion of the string matching part of dynamic programming. We will do a detailed pattern matching problem as a separate lecture where we will study those algorithms. But dynamic programming, there are other problems related to dynamic programming that we shall see later on. And these problems are, we will see there are several problems like the knapsack problem, we will see many matrix and graph path problems, we will see optimal weighted data structures like binary search trees, and dynamic programming, its whole tenet which comes up from this, will be studied in details in several places. With this, we come to the end of this lecture. We look forward to your suggestions. We look forward to you to see the large number of variations that occur in practical problems which are related to such alignments and string matchings and the way these are done. We have done the classical dynamic programming algorithm, but this is an open field for you to investigate. With this, we come to the end of this lecture. Thank you very much.